In this short video, we're going to talk about a phenomenon called total internal reflection, um, which has to do with both refraction and reflection. Um, so let's get on to it.
So we get some really interesting results when we start looking at how refraction works. Um, in this image, we can see uh, a ray coming in to a change in medium, right? A lot of times, some of that is reflected and some of it is refracted. Okay, so a portion of it gets through that interface, and a portion of it gets reflected back. And you can see that when you see light going into a window, right? You can see a little bit of the reflection, but also some of that light is going through the glass so that people on the inside of the glass can see what's happening outside. Um, Here we can look at this and say, okay, which one of these has the larger index of refraction, right? And it would be this medium, right? Because our angle here is steeper, it's closer to the perpendicular, so we know our light is moving slower here. And here, that angle is bigger, so we know the light is moving faster. What happens as I move from this slow medium to this fast medium as I make theta 1 bigger and bigger, right? If I made this bigger, this is going to get even steeper, right? At some point, it's going to point in this direction. That is called your critical angle, okay? So if I creep theta 1 larger and larger, you're going to reach a point called theta critical where the refracted rays go perpendicular to the surface. Why is this important? What it does is it means you get what's called total internal reflection. So no longer are you getting any light going through that change in medium, but in fact all of it is being reflected back. So here we have an image of, here's our critical angle, the dotted line. We've made theta 1 bigger than our critical angle, right? And that means everything gets reflected back into our slower medium. And this is key here, with no loss of intensity, okay? So here you're going to lose some of the energy from that light that's going refracted. Here everything gets internally reflected. And this is actually a cool image over here. So you have incoming light that hits a mirror or something with different angles. You can see the light moving from the slow material into the fast one. It gets refracted a little bit, it gets refracted more, and then at some point it all gets reflected back into the water. And here you can see a little bit of this is being reflected back, right? But here everything gets reflected. And this has a lot of important uses because you're not losing energy. I mean, and those are rare physical situations that we can say we don't lose any of our intensity. So we can find that use Snell's law to find that critical angle. But just to give you an example of one way that total internal reflection is used is when you use an endoscope, which is a long flexible camera that you can look at things in the human body. My wife actually had one of these done of her stomach, and usually they give, you get some sort of sedative, but she decided she wanted to watch. So she lived with the pain of having them, stick this thing down her throat so that she could see the inside of her stomach. But what happens here is you shine light. In this case, an endoscope has two of these tubes, right? One of them, you shine a light through there, it bounces all the way down the tube and lights up whatever you're looking at. And then there's a second one that's a camera that takes that light back. That image bounces all the way through the tube, and you can take an image, even though this tube is flexible and quite small. So that's really interesting. What does that mean about your N here and your N here? This N has to be large, right? It's going to stay within the slower material when you have total internal reflection. So you have to design this so that the N of your internal material is larger than the N of your outside cladding.